recording the lecture. Okay, so this course is about randomized algorithms. And this is an extremely important, very sort of also contemporary topic in theoretical computer science. Indeed, almost, I'd say the vast majority of recent developments involve algorithms that use randomness. And this course is about sort of, I guess, fast introduction to the analysis of randomized algorithms. So this is really, the course is on, it's the analysis and design of algorithms that use randomness. And I want to sort of state something here which is very important, which is often a point of confusion with people who are more used to sort of statistics and statistical models of input. Typically there is no assumption on the input. The algorithm and guarantees are worst case over inputs, and the probabilities are over the randomness of the algorithm. So this is a very important point here, and often a point of confusion. There is no assumption on the input. I'm not going to assume that the input comes from a distribution and then do an average case analysis. That in the TCS world is often called average case analysis. Here in randomized algorithms, the algorithm itself is worst case over all inputs. So it is meant to work for all inputs. So there is no statistical or no stochastic assumption on the inputs. All the probabilities and the stochasticity is over the randomness of the algorithm itself. And I'll give you examples over here, but I want this point to be very clear. And if there's any point of confusion, again, please feel free to sort of just stop and ask me questions. But it is important to note that the probabilities are over the randomness of the algorithm. There is no randomness over the input. So the guarantees, although I'm not going to write this out in this form explicitly, is for all inputs, the probability that the algorithm, succeeds or has a low runtime is at least blah. This is what the guarantees look like. You see the for all inputs over here. If one were to say the probability over the inputs, that means that you have some assumption, distributional assumption on the inputs. Here, there is no assumption on the inputs because we're saying that we want this guarantee to hold for all inputs. And therefore, the randomness of the algorithm is independent of the input. And you'll see an example here when I talk about randomized quicksort. Okay, so any questions on that? Hopefully that is clear. Okay. Now I'm going to start, and I'm just going to dive directly into the analysis of two randomized algorithms that are really gems. These are like really beautiful analyses using actually very simple facts in probability theory. And one of the amazing things about randomized algorithms is that the amount of probability theory that goes in, is for many results is not that sophisticated, but the analysis itself is extremely clever, and it can be surprisingly short if you know how to use the right probabilistic tools. So I'm going to start with a basic fact that probably most of you are already familiar with. And so let me start with just two basic facts, and I'm going to actually analyze two algorithms using these facts. So two basic, extremely important facts. And just to be clear, so when I usually use X, Y, Z, these sort of capital letters, I mean random variables. Indeed, most of my random variables, unless I say so otherwise, most of the time, these will be discrete. Often they will be non-negative. They will be discrete, non-negative random variables. That is typically the kinds of random variables that we will be dealing with in this course, although that is not always the case. But by and large, when you think random variable, you should be thinking of a discrete random variable like, you flip a number of coins and it's the number of heads that pop up. Something along those lines. Okay? So one of the most basic properties of a random variable is the expectation of the random variable. So this is the expectation or the average value of the random variable x. And what is the expectation of the random variable? It's the sum over the probability that x takes the value little x times x, and where x in this case is over whatever domain it is. In this case, typically it would be something like maybe natural numbers, 0 or whatever have you, but typically this sum is over whatever domain x lies in. Okay, and in this case I'm looking at discrete non-negative random variables, so you can think of these are basically just going to be whole numbers. Okay, this is the expectation, which is the average value of a random variable, right? So a fundamental fact about random variables is known as linearity of expectation. And what linearity of expectation says is this rather simple fact that given two random variables x1 and x2, the expectation of x1 plus x2 is the expectation of x1 plus the expectation of x2. There is no assumption on the random variables. Okay? I do not need these random variables to be independent. All I have are just two random variables. The expectation of the sum is the sum of the expectation. So I'll actually just sketch out the proof of this fact, just to sort of warm things up. But it is incredibly important to note that there is no assumption on these random variables. So, they could be highly dependent, they could be correlated, these could even be the same random variable. And just to see if x1 was equal to x2, then this is sort of clearly true. Right? So this is, it's true, just to take a simple example, when the random variables are identical, the expectation of 2 times x1 is obviously the expectation of x1 times 2. Okay? So let me just write out the proof of linearity of expectation. And in general, you can generalize this proof to the sum of any finite number of random variables. Okay? So let me make this out. So let's just look at the proof of this fact. So the expectation of x1 plus x2. So what is this? This is really the summation over, again, the summation is over the domain of all possible, is over the, I'm sorry, the domain that these values exist in. And let me just let script x be the domains of x1 and x2. For simplicity, assume that they are in the same domain. And if x bothers you, you could think of it, they could be real numbers or natural numbers or whatever have you. So it's a summation of x in whatever domain you have times the probability that x1 plus x2 takes the value x times x. Right? The probability, I'm just writing out the definition. Now, it's going to be convenient for me to split this sum as follows. I'm just going to say, I'm going to write this as a sum of x1 in x, of x2 in x, of x1 plus x2, times the probability of x1 is equal to x, and probability that x2 is equal to little x2. So I'm just saying, look at all possible values of x1. Let me call that little x1. Look at all possible values of x2. Call that little x2. And what we have here is we simply say that consider the joint probability that capital X1 takes the value little x1. Capital X2 takes the value little x2. The joint probability times this, the total value, which is x1 plus x2. So does this make sense? Okay?
Yeah.
Note that this is not necessarily equal to the probability of x1 is equal to x times the probability of x2 is equal to x. This is not necessarily true. Why is this not necessarily true? Someone want to speak up and say, why is this not necessarily true?
Because they can be dependent.
Because they can be dependent, right? I did not assume anything about the random variable. So all I can write is this. And now I'm just going to sort of move that over there. Now let me split this sum as a summation of x1 in x, x1 times the probability of capital X1 being equal to little x1 and capital X2 being equal to little x2 plus the summation of x2 in x of x2 times the probability of x1 equal to little x1 and x2 being equal to little x2. I'm sorry, I should probability of x1 in x and the x2. Right? So I'm just taking this double summation and I'm splitting it up at that sum to get these. And now let me just look at this term over here. Okay, so I'm just going to expand that term out. So I'm going to write this out as the summation of x1 in capital X times x1 times the summation of x2 in the domain of the probability of x1 is equal to x1 and the probability of x2 is equal to x2. Does that make sense? Right? So all I did was, this was a double summation. I'm sorry, I compressed that double summation into a single summation and expanded it back to a double summation. Just saying this term over here, that term over there, I wrote it as a double summation over x1 and x2, and I moved the summation of x2 inside. So it's a summation of x1 is x, little x1, and the summation over little x2 of this joint probability. Yes? So far so good? Okay? Now, let me introduce, I said I would be doing two basic facts. The second basic fact that I wanted to do, which I'm going to sort of fold into here, is basically conditional probabilities, right? So we know that the probability of two events, if you have the probability of two events, you can write this out as the probability of the first event happening times the probability of the second event conditioned on the first event. This is your conditional. Right? This is the conditional probability. Let me write this out in that form. x1 and x, summation of x1. I can write, this is the intersection of these two events. I can write this out as the probability of x1 and x1 times the probability of x2 being little x2 conditioned on capital X1 being small x1. Now I can move this outside the summation and I get this. Little x1, the probability of capital X1 being equal to little x1, and the summation of x2 being an x, of the probability of x2, capital X2 being small x2, and capital X1 being small x1, conditioned on this. Okay, does this make sense at this point? Now, do you see how to complete the proof? What is this? This is the sum of probabilities of capital X2 being small x2 conditioned on some fixed x1. Does someone want to shout out what this probability is? 1, right? So this probability is just 1. And therefore this is just the expectation of x1. Analogous argument will show that the expectation, or sorry, this quantity is simply x, the expectation of x2. Right? So this thing over here was the expectation of x1. This expression here is the expectation of x2. I'm not going to write it out, but it's basically just the same argument. And what you get is that you get the overall sum. You will get that this quantity can be expressed as the expectation of x1 plus the expectation of x2. Okay? So this is the proof of linearity of expectation. Okay? So the basic facts that we're going to use in today's analysis are really simple. It's just linearity of expectation, and we're going to use conditional probabilities. Okay? So that's fact 1 over there, and this was fact 2. Okay, any questions?
Yeah, can I ask a question?
Yeah, go ahead.
If x1 and x2 are they belong to different domain, does it still hold?
Well, then, I mean, the sum doesn't really make sense, does it? If x1 and x2 are in different domains, then how do you interpret the sum? Unless, you could basically let this be sort of the union of the domains. Does that make sense? I mean, in this case, we are basically mostly going to deal with real valued random variables, so this is not an issue. But you could apply this even to vectors. But it doesn't make sense to sort of add vectors on two different dimensions, if that makes sense.
Yeah. Thanks.
Okay. To continue, okay, so now that you have linearity of expectation and you have conditional probabilities, I'm now going to present to you 2 gems of randomized analysis. The first one is the analysis of randomized quicksort. Is the analysis of randomized quicksort. Okay, sorry, just give me 1 second. What I'm going to do is I'm going to use my microphone over here because I'm getting some disturbance, and just going to Okay. Can everyone still hear me?
Yeah.
Yeah? Okay, very good. Okay, so let's do the analysis of randomized quicksort. So let me just, let's recall what randomized quicksort is. It's basically quicksort where you pick the pivot at random. So I'm going to write this. So I'm going to say A is an array of numbers. Okay, A is an array of numbers. N is going to be the length of A. Now, because I'm going to assume that most of you are familiar with randomized quicksort, I'm not going to write this out in sort of gory detail. So how does randomized quicksort, which I'll call RQsort, work? So the first step, of course, if n is equal to 1, then just output A, right? That's the base case. If not, what you do is you pick a uniform, a UAR. So I'm going to use UAR a lot, which I mean uniform at random. Pick a UAR pivot in A. Call it X. So you pick a uniform at random element in A called the pivot, and we're going to call that X. And then comparing X with all elements of A. So you compare X, right? So you start with your array, you pick some random element X, then you compare every element with X, right? So comparing X with all elements of A, partition A into L, X, R. L is equal to elements, I'll say at most X, excluding X. R is equal to elements, I'll say greater than X, right? So you partition the array into 3 parts: L, X, R. L, these are all the elements in the array which are at most X, excluding X, right? So you don't want to sort of include X as well. So this is everything that is less than equal to X, and this is everything that is greater than equal to X. Okay, so sorry for this being a bit messy here, and I'll say step 4 is to just call RQsort on L and randomized quicksort on R, right? So this is randomized quicksort. It should be, you've already seen that randomized quicksort essentially is going to sort any input. There is no randomness on the input. The randomness is only over the algorithm. Okay? So randomized quicksort. Any questions about that? Okay. I'll continue. Let's analyze randomized quicksort. So the question is, what is the expected running time of RQsort on an array of length n? This is what we're going to analyze. This would be the running time analysis of randomized quicksort. Okay? The expected running time of randomized quicksort on an array of length n. What is the worst running time of randomized quicksort in an array of length n. What is the worst running time?
N squared.
N squared, right? In the worst case, by worst case, I mean if the worst case over the randomness, the running time would be n squared, because the pivot might just be the first element or the last element, in which case it's going to be bad. Now, we hope, now if you recall the analysis of merge sort, you'll say, well, on the average, L should be approximately the same as R should be n over 2. That's what you hope. So we should get T of n at most 2 T of n over 2 plus O of n on average. And of course, this was the time to compare the pivot with all other elements. So you hope that there should be something like n log n. Now, if you try to directly do this analysis on average, so you could say, well, on the other hand, what you can actually get is you can say that T of n is, and if you sort of walk through this analysis, you should be able to say something like T of n is something like, I guess it would be, depending on how you chose the pivots. So you would get something like this: T of I plus T of n minus I minus 1, the summation of this over all I going from 1 to n, plus O of n. Does this make sense? So this is what you would get on the average. But if you actually sort of did this math more directly, you would say that the probability, right? So the probability that L has size I, the probability that L has size I is exactly 1 over n. So with probability 1 over n, like if you picked X to be exactly the I plus first element in sorted order, L would be of size I, R would be of size n minus I, and you would get something like this. Does this make sense? And you can go and try to sort of analyze this directly. It is possible, but it's a bit of a pain. And what I'm going to show to you is Karp's analysis using linearity of expectation, which is a work of art. Instead of trying to directly analyze the running time through a recurrence, what I'm going to do is, so let me actually first start by saying, instead of the expected running time, I'm going to analyze the expected number of comparisons. And it's the same, like up to big O factors, the number of comparisons is the running time. Like if you look at Quicksort, you can see that the number of data moves is basically O of the number of comparisons. So let me focus on the number of comparisons. And let me define, so for I less than j, I'm going to define a random variable called xij. Okay, this is an indicator random variable. It's an indicator random variable for, okay, so now let me tell you exactly what it's for. So this is A. A is not sorted. Let me instead say B is the sorted version of A. And this is going to be more convenient for me to deal with. Okay, so B is just the sorted version of A. I'm going to define the indicator random variable for Bi being compared with B of j in a run of randomized quicksort of A. Does this make sense? So I'm looking at the run of randomized quicksort of A, and I'm looking at the ith element and the jth element in sorted order, and I'm defining an indicator random variable for those two being compared. What does an indicator random variable mean? It is 0 if bi is never compared with b of j, and it's 1 else otherwise, meaning that it's 1 if the comparison is made, and it is 0 if the comparison is not made. So this is basically, this is also called a Bernoulli. It's a Bernoulli random variable. It's basically just, it's either 0 or 1. It's an indicator. Okay, any questions on what Xij means? Okay. What is the total number of comparisons made by randomized quicksort in terms of Xij? Someone wonder?
Just the sum.
Just the sum. So the total number of comparisons is simply I less than j less than n of Xij. Right? What is the expected total number of comparisons? Well, it's just the expectation of the sum. Okay? And now, here's the clever bit. When you think about the Xij's, they're all correlated with each other. On the other hand, by linearity of expectation, this can be written as follows. This can be written as follows. This is linearity of expectation. Now this seemingly very simple step does this magical thing that instead of trying to figure out the total number of comparisons and understanding how they're all correlated with each other, which is what it seems like you need to do to understand the total, all you need to do is to bound this expectation, which is the probability, which is simply the expected value of Xij. Now, because Xij is just an indicator, this is exactly the same as the probability that Bi and Bj are compared. Right? The expected total number of comparisons, that's exactly the same as the sum of probabilities. So if I can bound these probabilities, then I can bound the total number of comparisons. Any questions? Okay, let me continue. So I need to sum these probabilities and I would get the total number of comparisons. Okay, so and I guess I want to emphasize something here, which I said it once, but I'll say it again because this is an important point. These random variables are correlated. But when I do this analysis, somehow magically, I don't need to worry about the correlation between these things. And this is sort of a very, very important part of the analysis of randomized algorithms, is when you try to write things in terms of random variables, when you try to write the running time in terms of a sum of random variables, you can immediately use linearity of expectation to analyze each of these events separately, as opposed to having to analyze the correlations between these events. Okay, so now let me do sort of continue with the analysis. Now I'm going to prove a claim, and from this claim the analysis will then follow. The claim is that the expected value of xij, which is the probability that bi is compared with bj. I'm going to prove to you that this is exactly 2 divided by j minus I plus 1. So I can nail it down exactly. It's 2 divided by j minus I plus 1. So let's just understand what this means. This is inversely proportional to j minus I. Okay? Let me sort of go back to this picture here. Let me go back to this picture here. So the further apart I and j are, the smaller the expectation is. At an extreme case, when j minus I is equal to 1, this is equal to 1, which makes sense. If you take any two elements that are neighboring in sorted order, any sorting algorithm has to eventually compare them to decide which one goes before the other. But if you take two things that are far apart, then Quicksort may avoid comparing them by choosing a pivot in the middle. We'll see this more specific. We'll see this in the proof. But I want to emphasize over here that the probability that bi is compared with bj is inversely proportional to j minus I. The further apart the elements are, the less likely they will be compared. Okay. Okay. So now let us continue with this analysis. So what you'll see is in the books, which is in Motwani-Raghavan and Mitzenmacher-Upfel, the proof of the statement is usually expressed as a symmetry argument. And I will show you the symmetry argument. But I feel that it's sort of it always worried me as a student that it was not as formal as I wished it to be. So I want to show you some of the exact formalism on how I would write this proof down. But I think the symmetry argument is important to understand the intuition behind the proof. So let me actually show you the intuition behind this proof. So here's our array, and this is B. So here's I and J. Okay. Now let's just look at the very initial run of Quicksort. Remember, Quicksort is being run on A, not on B. I'm just using this to sort of look at the elements of A. So A is going to first pick a pivot uniformly at random. Suppose the pivot lay in this region here. Suppose the pivot was less than bi. So I'll say if the pivot was less than b of I, then what? What's going to happen? Any comments, any thoughts? What's going to happen if the pivot was smaller than bi? Just in the running of Quicksort.
They won't be compared in that step.
They won't be compared in that step, but there's something more important. There are going to be two
same partition. Yeah, they'll wind up in the same partition.
Exactly.
So they're going to get eventually compared.
Eventually, they may or may not get. We don't know.
May or may not.
What we do know. So good. So what we do know is bi and bj will end up in the same recursive call. In other words, bi and bj end up in R. If the pivot was more than bj, then bi and bj end up in the left side. Again, let me just show you what I mean. If the pivot was less than I and j, then both elements end up in R. If the pivot was more than both I and j, both elements end up in L, the left part of the partition. So the interesting case is really if the pivot lay in between. So now if the pivot lies in here, now what's going to happen? So the pivot was chosen between bi and bj. What if the pivot...
And they're not going to be... Sorry.
Go ahead, no.
Then they're not going to be compared then, because they'll wind up in different lists, and they're only going to be compared to...
So yeah, let's be careful. So if they're between... Okay, so remember, this is not a strict inequality. So if... Okay, so now let's look at this case. I'll say if the pivot is equal to bi or bj, then of course there is a comparison, because every element is compared with the pivot. So if the pivot is equal to bi or bj, xij is equal to 1. And if the pivot is not equal to bi or bj, so if the pivot was chosen in the middle, bi is going to end up in L and bj is going to end up in R. And in this case, xij is equal to 0. This is really important that we understand this. So I'm going to walk through this again, because this is the crux of the analysis. Okay? So saying that if the pivot was less than bi, then both of these end up in R. Okay, I don't know. What's going to happen? It's going to happen further down. If the pivot was more than bj, then both of these end up in L. Things are going to happen somewhere downstream. But if the pivot lay between bi and bj, if the pivot was actually equal to bi or equal to bj, then of course they will be compared, because every element is compared with the pivot. If the pivot was strictly in between, it was not bi or bj, it was in between, then bi ends up in L, bj ends up in R, and they will never be compared because they end up in separate partitions, separate parts of the partition. And in that case, xij is 0. Is this clear? Now tell me, conditioned on this event, what is the probability that xij is equal to 1? Conditioned on this.
2 over j minus I plus 1.
2 over j minus I plus 1, right? Because there are j minus I plus 1 elements in here, and this is 2 of those pivots. And so, the probability that xij is equal to 1 conditioned on the pivot being in bi comma bj is 2 over j minus I plus 1, which is basically the same thing. Now, of course, this was a conditional probability. But what you can basically show, essentially by induction, is if you're in any of these cases, it's going to keep going down until you hit a case when the pivot is actually in between. So another way of saying this is, as long as the pivot is not in between, the decision of whether bi and bj are compared is deferred to another call. At some point, a call, one of the recursive calls, is going to make a decision. And when it makes that decision, that is, when the decision is made, you have this probability. This is the intuition. Indeed, this is usually what is given as a proof. It's just said that by symmetry, because any of these are equally likely to be the pivot, you get this probability. I prefer, let me just sort of state a little bit on the formalism as to how you would do it, how I would write it formally, with the caveat that this is not the way that it is written in books. So for the scribe, what I would like is for you to basically write out what I'm going to say further on more formally. So I'm not going to write out the proof in all of its gory detail, because that would be somewhat of a waste of time. As long as you understand this idea and understand the formalism, you should be able to recreate the proof. And essentially, more formally, I think the most natural thing to do would be an induction over the size of the array in a recursive call. Does that make sense? So, every call to quicksort is over an array, and so we'll just do induction on the size of that array. Does that make sense? Okay? And so what you can say is that the base case, I'll say that the size is exactly j minus I plus 1. This is when I and j are the first and last element, right? This is the base case because the array cannot be any smaller than that. No recursive call that contains I and j can have anything less than j minus I plus 1 elements. So when the size is exactly j minus I plus 1, then the pivot is always between bi and bj for that recursive call. And so in this case, the expected value of xij being 1 is exactly 2 minus j plus I, as mentioned earlier. And so for the induction, what you could say is that the probability of xij is equal to 1 can be broken up by conditionals as the probability of xij is equal to 1 conditioned on the pivot being less than bi times the probability that the pivot is less than bi plus the probability that xij is 1 conditioned on the pivot being greater than bi times the probability that the pivot is greater than, bj plus the probability that xij is 1 conditioned on the pivot being inside bi comma bj, the probability that the pivot is in bi comma bj. And what you see here is that this is equal to 2 divided by j minus I plus 1 just by the arguments we gave earlier. Right? That was exactly what we argued. This and this, both of these are 2 divided by j minus I plus 1. And why? Why are these also 2 divided by j minus I plus 1?
By the induction hypothesis?
Induction. Because when the pivot is less than bi or bj, then both bi and bj end up in the same recursive part. Right? They end up in the same part of the partition which is smaller. And so this is induction. So putting it all together, regardless of these probabilities, because each of these is exactly the same, this whole thing is 2 divided by j minus I plus 1, and that gives us the end of the proof. That gives us the end of the more formal description of the proof. In general, what is simply said is, just by symmetry, you know that the first element between bi and bj plus 1 effectively determines, the first pivot amongst them determines whether they're going to be compared. So what you have is the probability that bi is compared with bj is 2 divided by j minus I plus 1. Okay, any questions? Okay, if not, I will continue. So now that we have this, let's go back to what we had earlier. Remember, I said the total number of comparisons is, by linearity of expectation, the sum of expectations. And then we have that each expectation is 2 divided by j minus I plus 1. Right? So we know what each of these expectations are. We have this. Now I'm just going to plug that in over there, and I'll be done. So the expected total number of comparisons is equal to the sum over I less than j of the expected value of xij. Okay, I'm just going to write this. I'm going to first take the sum of I going from 1 to n, and then some j going from I plus 1 to n. Remember, this is 2 divided by j minus I plus 1. Right? 2 divided by j minus I plus 1. Does that make sense? Now note that I can rewrite this, I going from 1 to n. I'm just going to express this difference over here as k. Yeah, so I can rewrite this. Remember, j minus I starts from 1. So I can say it goes from 1 all the way up to, finally, j minus I is going to be n minus I. So it's 2 divided by k plus 1. Which, let me sort of write out over here, is I going from 1 to n. Maybe just to make it more conveniently in a form that you would all recognize, I'm just going to pull this 2 out over here. And I'm just going to write this as, I'm just going to say k is going to go from 2 to n minus I minus 1 of 1 divided by k. What's that? Any comments on what that is?
The harmonic series.
It's the harmonic sum. If I add a 1, I get the harmonic sum. Right? So this is basically the n minus I minus 1th harmonic number minus 1, because I have the first one out there. And asymptotically, what is a reasonable approximation for the harmonic number? What's a reasonable approximation for the harmonic number?
ln.
Log of n. This is approximately log of n minus I minus 1 plus some theta of 1. Right? So this is approximately log of n minus I. So I can very simply, if I just wanted to give a simple upper bound, I would just say this is I going from 1 to n, log of n plus theta of 1, which is O of n log n. So the expected number of comparisons is O of n log n, but even better, I can write it out as a precise expression, which is quite remarkable. Given that if you really think about how randomized quicksort works, all the further decisions, the arrays, there's sort of all this dependence, because the initial calls determine the size, which determine further sizes, so on and so forth. But I can write out a fairly precise expression for the expected number of comparisons, and I get it down to O of n log n. Okay? So at this point, what I'm going to do is I'm going to pause for about 5 minutes, and I will take any questions that you have for the next 5 minutes before I go on to the next topic. Okay, so let's continue now. So now that we did quicksort, I'm going to give you another algorithm. This is, again, given in Motwani-Raghavan and Mitzenmacher-Upfel, and this is like this is an absolute book proof, right? As you know, Paul Erdős had this notion of beautiful proofs coming from the book with a capital B. The following is really a book proof, and it's an algorithm that never ceases to amaze me, and it's something that I think anyone who does randomized algorithms should see. And this is Karger's mincut algorithm. Okay. Now pay attention, because the proof is incredibly slick and short, but is sort of profound. Okay, so what is the min-cut problem? Min-cut problem is you have a graph G. You want to find a set of vertices S such that the edges going from S to S complement is minimized. Okay, so what you're doing is you have a graph. Here is S, this is S complement, this is called the cut, and you want to minimize the cut. So this is called the min-cut problem. Find S, or you could even say find the value. Find the minimum cut value. So, and I'll use n for the number of vertices. It is not obvious that a polynomial time algorithm exists. It's not obvious, although it does exist. It can be done in polynomial time. And if you look at a deterministic polynomial time algorithms, typically they're based on max flow min cut. They're complicated. The analysis is tricky. This is not an easy problem that you want to show for which you want to give a polynomial time algorithm. But Karger gave this polynomial time algorithm. It's a randomized algorithm, which is so deceptively simple, and the analysis is so deceptively short. So let me show you what the algorithm is. Before, I need to tell you about a particular operation on a graph that I'm going to call a contraction. Contraction. What is a contraction? So given an edge E, to contract E means to basically, let's say this is U and V, to create a new vertex that you could call U comma V that has the same edges going out. Okay, that is what a contraction is. This is what it means to contract the edge. Okay. Now I want to sort of also state that I'm going to assume, let me assume G is a multigraph, meaning G has parallel edges. So G has parallel edges but no self loops. So I'm going to assume, multigraphs can have self loops. I'm just going to assume that the graph can have parallel edges, and you'll see why I need that. So my graph could look something like this. Okay? When I perform the contraction, I'm going to keep parallel edges. So for example, if let's say that they had a common neighbor W, I will make W have two edges. So when I contract this edge, both of these edges remain. I only throw away the self loop. So when I contract, you can say, imagine that I delete that edge, but I do not delete any other edges in the graph. So I will keep parallel copies of all the edges. Okay. So G is a multigraph. G has parallel edges but no self loops. So for example, if I were to contract this edge E, what I would get is I would get a graph with 3 vertices that looks like this. So let me number these 1, 2, 3, and 4. So this is 1. This is like the contraction of 2 and 3, and this is 4. This is what an edge contraction is. So this is contract E. Now let me describe to you Karger's mincut. So just to make sure that you understand and we're all on the same page, when you contract the graph, how many vertices are left? So let's say you start with a graph with n vertices. If you apply one contraction, how many vertices remain?
N minus 1.
N minus 1. Right? The number of vertices goes down by exactly 1. Karger's mincut algorithm is going to basically work as follows. It's going to say while G has strictly more than 2 vertices. We'll discuss a little later on how to implement this using the right data structures. That is not as important. I first want to give you the randomized analysis. While G has strictly more than 2 vertices, pick a uniform at random edge E in G and contract E. Right? So what you do is really simple. You simply pick a uniform at random edge and contract it. Now, if you perform contractions, you keep reducing the number of vertices. So you keep doing it until there are 2 vertices left. So once this loop ends, you have 2 vertices with, sorry, just give me a second, let me get another pen. So when you have 2 vertices left, you're basically just going to have these 2 vertices with lots of parallel edges between it. So at the end, there's only one cut that's left, which is this. So you simply, the output, the number of edges between the remaining 2 vertices as the mincut, value. That's the algorithm. That is the algorithm. You pick a uniform random edge, contract. Keep doing a series of contractions. At the end, you're going to have 2 vertices left. You have edges between these 2 vertices. You simply output that number as the mincut value. Now you look at this algorithm and you say there is no way that such an algorithm can work. Right? Especially for a problem that is as deep and sophisticated as mincut, it just seems like there's no way this is going to work. And remarkably, we'll show that this algorithm actually has a non-trivial probability of success. So does the algorithm make sense? Does the algorithm make sense? Any questions? Okay, then I'll continue. So let's do the analysis as follows. So let's fix a mincut that I'm going to call C. Right? So you start with your graph. There's some mincut C. So as long as we contract edges not in C, the mincut is preserved. So as long as we can pick an edge that is not in the mincut and contract it, things should be fine. So what we need to do is, what is the probability that no contracted edge is in C? And by no contracted edge, remember there are n minus 2 contracted edges. right? N minus 2 contracted edges. Okay? And this is exactly the probability that the mincut is output. So if no contracted edge is ever in C, so if we always were to pick edges that were not in the mincut, then in the end, what this Karger's mincut algorithm will output is the true mincut value. And so we need to understand. Yes?
Someone asked in chat, but what happens if you contract two nodes where they have parallel edges between them?
Oh, what happens if you contract something that has parallel edges? Let's go back to this picture. So let's just say there were parallel edges over here. Remember, we delete self loops. So all of these would become self loops, and we would just delete them. Does that make sense?
But so why do we say at most n minus 2 contracted edges? Or do we not count the extra deleted self loops as contracted?
No, I'm just saying that there are n minus 2 contractions.
Okay.
Right? And so every contraction corresponds to an edge. Does that make sense? When you perform a contraction, you delete the self loops. So when a contraction is performed, like technically all of these would become self loops, but you just delete the self loops. And then you pick a uniform at random edge and what's left. Any questions? So by the way, feel free and stop and ask me if anything, if you have any questions there. So we need to understand, we need to bound the probability that no contracted edge is in C. Towards that, I'm going to define some events. So let me say that the event EI, this is the event of avoiding contracting an edge in C when there are I vertices in the graph. So this is just simply saying that in each of these iterations. So let's look at the iteration when there are I vertices left. So this would technically be the n minus I minus first or n minus I minus 2 iteration. So consider the event of avoiding and contracting an edge in C. So at every stage of the algorithm, you're picking a uniform random edge. And you want to say when you have I vertices left. So remember, at this point, the graph could look something like this. Right? So you're going to pick a uniform at random edge and you want to avoid C. And EI is the event of avoiding the cut edge in that iteration. So what is the probability? I can write this probability as the probability of the intersection of all of these events. So there are going to be 3 vertices up to n. This, right? So when I start, I have n vertices. Then I have n minus 1, n minus 2, n minus 2. I go all the way down to until when I have 3 vertices left, I apply a contraction. When I have 2 vertices left, there's no contraction left to do and I output the mincut. So I have this expression over here. Now, I'm going to basically expand this out using conditional probabilities. I'm going to say this is the probability that I did not contract, that I avoided the mincut in the iteration corresponding to n, that is the first iteration, times the probability of I minus 3 to n minus 1 of EI conditioned on En. Right? So this is the probability that I did not contract a mincut edge in the first iteration where there are n vertices. Conditioned on that, I didn't do any bad contraction. So think of this being a bad contraction, and this is the event of not doing a bad contraction. So let's call this a good contraction. This is the probability of doing good contractions in all the other iterations. I can keep continuing this process and breaking it up. So what I could do now is I could say this is the probability of this, of the nth, times the probability of n minus 1 conditioned on that, and times the probability of the union of I going from 3 to n minus 2 of E1 conditioned on good contractions in the last two iterations. So this is the probability of a good contraction in the very first iteration, the probability of a good contraction in the second iteration conditioned on doing one in the first iteration. I'm sorry, this should be not a union, but it should be an intersection. And this is the probability of doing good contractions in all the remaining iterations conditioned on doing good contractions in the first two iterations. So I keep continuing this chain, and what I'm going to get is the following. I get the probability of no contracted edge is ever in C, as I can write this out as follows. Probability of doing a good contraction at the last step. I'm going to write this out sort of in, let me write it out somewhere in gory detail here. This is the probability of a good contraction in the second iteration, conditioned on doing it in the first. A good contraction in the third iteration, conditioned on that. Times, this kind of keeps continuing. In general, what you get is the probability of doing a good contraction when you have I vertices left, conditioned on j going from I plus 1 to n of ej, meaning that this was doing good contractions in all the graphs up to when you had I vertices, and this is the probability of doing a contraction in the ith when you had I vertices left, and this is going all the way up to doing a good contraction when you have 3 vertices left, and this would be j going from 4 to n. Does this make sense? So if this doesn't make sense, please stop me, because at this point now we're going to do some magic. All I have done is I have rewritten the probability of getting a contracted edge, of never contracting an edge in the cut, as this product. Any questions? Okay. Now let me continue with the analysis here. Let's look at this quantity and let's lower bound it. So there are I vertices in my graph at this point. There are I vertices. This is a multigraph, right? What is the probability that I do not get a cut edge? So this probability is exactly equal to, this probability is exactly equal to 1 minus, remember there is a mincut C divided by the total number of edges at this iteration, the total number of edges in this iteration. Okay? Does this make sense? So the probability is simply 1 minus the probability that you actually did get an edge in the cut, which is C divided by the total number of edges. Questions? Okay. How many edges are in this iteration? Now since C is a mincut, all degrees are at least C. Because if you had a vertex whose degree, if the degree was less than C, then this would become a mincut, meaning that the mincut value is actually strictly smaller than C. But we said that the mincut is C, and we conditioned on contracting edges that are not in the cut. So we preserve the mincut up to this point. And at this point, if there is a mincut, all the degrees have to be at least the mincut value. Otherwise, here's a cut which has value less than C. Does this make sense? This is really important. Since C is a mincut, all the degrees are at least the size of C. Questions?
Just to clarify,
Yes.
The degree is in this iteration.
The degree is at this point. The degree at this point, right? At this iteration. All of this is sort of conditioned on the choices that you made so far. So you've made a set of contractions, and now I'm looking at what is the situation at this point. Yeah? So all the degrees are at least C. There are I vertices in the graph. Can you tell me how many edges there must be? What is a lower bound on the number of edges in the graph? You know that there are I vertices. And you know that all the degrees are at least C. So how many edges are there?
I times cardinality of C.
How many edges? Sorry, what was that?
I times cardinality of C
I-
divided by 2.
I times the cardinality of C divided by 2. Exactly how many edges? Well, it's at least I times C divided by 2, right? Because there are I vertices, all the degrees are at least C, so you have at least that many edges. Because that's the sum of degrees divided by 2. Okay, let's just plug this thing over there. So remember, I said the number of edges at this iteration is at least I times C divided by 2. So therefore, C divided by the total number of edges, right? That is at most 2 divided by I. Plug this in over there. This is at least 1 minus 2 divided by I. It kind of makes sense that I should never be 2. When I is equal to 2, this is 0. But when I is equal to 3, this is at least a constant. Okay? So now let's go back. Let's go back to this expression. For the ith term, we have a bound. And remember, this is the probability of finding the mincut. It's exactly the probability of finding the mincut. So let's go all the way here and say the probability of finding the mincut. This is at least the product of I going from 3 up to n of 1 minus 2 divided by I. Okay? And I'm just going to write this out as the product of I going from 3 to n of I minus 2 divided by I. Okay? And so now watch the magic. So write this out. N minus 2 divided by n times n minus 3 divided by n minus 1 times n minus 4 divided by n minus 2 times n minus 5 divided by n minus 3 all the way down to what's going to end up here is that. This cancels with this. This cancels with this. This cancels with this. So on and so forth. Until what you have is 1 divided by n times n minus 1. So the probability of finding the mincut is actually at least 1 over n squared. Okay, but you'd say, but that's such a small probability of finding the cut. Like, how can I use this to get an algorithm? This is tiny. But all you do is independent iterations of this algorithm. So what you do is consider the following. Repeat Karger's mincut. I'll say C times n squared times independently. Okay, C is a constant which I'll tell you to set. Okay, repeat C times n squared. Output the minimum cut seen, right? So it's quite easy. What you do is you say, well, you have this procedure. I'm just going to put an extra condition out here and just say, repeat this whole thing n squared times and just output the minimum that you ever saw. So this is, every iteration is going to give you a cut. You just output the minimum over all cuts that have been seen. So output the minimum cut that's been seen. And now if you look at this procedure, what is the probability of not getting the min cut? So in any one iteration, the probability of not getting the min cut is this, right? We just argued the probability of finding the min cut is at least 1 divided by n times n minus 1. So the probability of not getting the min cut is at least this to the power cn squared, right? Because you're repeating it so many times, and these are independent iterations. And so, you know, I let me just write this out as so I could write this as 1 minus 1 over n squared cn squared. Now just using the inequality that 1 minus x is less than e to the minus x when x is less than 1, or I'll just say x is less than 1, I can just say this is e to the minus cn squared divided by n squared, which is e to the minus c. So the probability of not getting the min cut, if I repeated cn squared times, is e to the minus c. So simple, if c is equal to 10, the probability of not getting the min cut is tiny. It's actually I even sort of looked up what this is. This is like 0.00005. So if you simply repeated the procedure 10n squared times, the probability of not finding the min cut is that small. It's tiny. And so that is Karger's mincut algorithm. It's a polynomial time algorithm. I did not discuss the data structures on how you implement contractions, but it is possible to do the contractions. It's possible to do them so that it's efficient. And so let me again just describe the algorithm to you all over again. So you start. As long as G has more than 2 vertices, you pick a uniform random edge and you contract it. And you output the number of edges remaining when you have 2 vertices left as the min cut value. You repeat this entire procedure cn squared times, and that's the algorithm. So you simply repeat the cn squared times and you output the minimum cut value ever seen so far. And that, we analyze, actually has an extremely high probability of success. Okay, so let me end with this. So I'll take questions now at this point. I'm just going to sort of stop the recording now. So I showed you the analysis of randomized quicksort. and of Karger's mincut, and most of this base has been taken, or effectively all of it has been taken from Motwani-Raghavan's randomized algorithms book in the first chapter.